Hello everyone, welcome to my course lesson Understanding Memoization in JavaScript. In this course lesson, we will learn how to use memoization to speed up our function calls in JavaScript. Also, we will learn how to implement a custom memoization script for global use in our application. Now let's begin. Memoization is a global optimization trick used generally in software development. It is used to speed up computer programs by storing results of expensive function calls to pure functions and returning the cached result when the same inputs occur again. We can use this same trick in JavaScript, but first let me show you in pseudocode the basic idea of memoization. Now let's say we have an expensive function like this with an input. Now this expensive function takes like more than 30 minutes to complete, and this operation run here also depends on this input argument. Now this function also is a pure function, meaning that it does not have any side effects or does not change anything outside of its scope or have a dependent outside of its scope. So it is purely self-contained function. Now, let's say we call this expensive function with an input, let me say 90. Now, this function call will run for 30 minutes before it completes. Now, yet again, we call the function with another input, let's say 20. It will run for 30 minutes to complete. Now, we call the function with an input 90 and it will run again for 30 minutes. Now, in total, it has run up to 1 hour 30 minutes. Now, look at what we have here. We have this input here and we have the same input here. Now, we can simply store the result of this operation somewhere and return it when the input occurs again, thereby reducing the time it takes for this function to complete. So from 30 minutes to just 0 seconds. The memoization logic occurs inside the expensive function or inside the function that we want to memorize. So now let's write out the pseudocode for the memoization logic. It looks something like this. Now see how it goes. First, where the function is called, it will check if we have the result of that input in cache. Now, cache is the storage in this function where we store the results from the operation done on the input. Now, this cache is called something like a key value dictionary or just like an object that we store the result of the operation against the input. So it's something like this in a key value storage. Now, where the key is the input, in this case 90, and then the value is now the result of the operation. Let me say after the operation based on the input 90 that we got 450. So we'll store the 450 will be stored in the value column. Now let's say we pass 20 again, and after it 100 was computed as a result, it will be stored like this. So now in this first if statement, now the lookup will be done on the cache first, which is this. Now it will check the cache to see if the keys or any of the keys match the input. Then if it does, it will return the value. Now it knows that yes, this input has been called before and it will simply return the value and skipping the compute operation. So now look at the second one. If yes, like we said, it returned the result. Now it just does the lookup on the key on the cache, which is here the key based on the input, and then return the, if it sees it, then it returns the value. So now in this line 3, if yes return the result, it will now skip this operation that will take 30 minutes. So the function will just return in an instance. So by doing this, we have reduced the performance or the operation of the function. Now reducing the time it takes to execute from 30 minutes, just 0 seconds, just an instant. So now the third logic, if no, compute the operation. Now, like if there is nothing stored, like let me say the input was 100, there is nothing here in the cache. So you just compute the operation, then stores the result in the cache and returns. Now it now stores the result here. Let's say the result is 500, it stores it here and then returns. So the initial call of the input with 100 will run for 30 minutes, but the next call with the same input will just return the result from the cache. So yeah, so that was happened here when we call this function with the input 90. Now the cache will be like this. So it will take a look at the cache with the input as the key. So it sees here that nothing is stored here. So it will do the operation and then store the result in the cache. Now it will just store 90 and store it in the cache and return. So this runs for 30 minutes because it does the operation here. Now on this next function, it does the same. The input is 20. Now it checks if we have the result, the input in the cache. It checks if we only have 90, we don't have 20. So it just computes the operation, stores the result. So this will run for 30 minutes. So it stores the operation 20, then with the against the value. Let me say 500 is the result of the operation. Now here it calls this third function. Now this third function we call with the input 90. It will check if we have the result of the input in cache. Now it will check against the key column to see if it will find a, a property that is 90. Now it will check, yes, we have 90 here. So it picks the value here and simply returns the result. So this compute operation will not run. So it will not take 30 minutes. It will just like take 0 second to complete. So it will return very fast. So you see, we have reduced the initial time of this execution of this three function from 1 hour 30 minutes to just 1 hour. Because these three functions will run for two of them, compute the time it takes for two of them to run to 1 hour. So now if we come here and call expensive function with value 100, now this will take 30 minutes also because this is the first time it's seen the input 100 and the input is not in the cache. So but after running it and completing the operation, to now store the result in the cache with 100 being the key and the result being the value, let me say 900, so that next time we call the function with 100, we'll just simply return it from the store without doing the long work of the operation that will take it 30 minutes to complete. So this is how memoization works. Now the, the thing for a function to be considered for memoization is that the function must not be an impure function. Like the function must be a pure function. We cannot memorize an impure function. An impure function is a function that has a dependency outside of its scope. So now this expensive function can only be memoized if it is a pure function and the result of this compute operation depends on the input. That's the only way it can be memoized. Otherwise, it cannot be memoized and it will return stale data or wrong data to us. Now, let's see in JavaScript how we can convert this pseudo code to JavaScript code. Okay, so here we implement our memoization logic here. So let's see how we are going to implement the catch. So for now, we are going to store it in a catch object. Object. So to be an empty object for now, let me disable this copilot. So we are using an object so that we can store it like this in a key value pair. So the object gives us a table for that. So the key, which is the property name, will be the input, for example 90, and the value will not be the result of the computation like this. So for now, we are going to make it an empty object for now. So we'll clear this. Now let's implement the logic. Now here we see check if we have the result of input in catch. Now what we're going to say, just write our if condition. Now since we know that the input is now the key, so we're now going to look for it inside the catch object using the bracket notation. So now this retrieves the value from this catch object. Now so inside it here, we know that we have gotten something from the cache, or we made a hit in the cache. So what we're just going to do here is just return the input. So it just returns it. Now here we know that there's nothing in the cache, that we made no hit here. So we're not going to run the computation. Now let's say we have a function, say some expensive computation function that will call, that will delay us for 30 minutes. Now we will not get the result in this variable. Now after that, we'll store it in the cache using the input as the key. So we're using the bracket notation to store it inside the cache object and passing it the result from here. Then we'll now return the result. So you see it, we have implemented the logic, the memoization logic. So this is the main memoization here, and also here we'll check the input in the catch object. If we made a hit, we're going to return that hit. So we'll now bypass this computation. Now we'll implement this some expensive computation function. Now I have already prepared code for it. Yeah, so it takes an input, creates an array of, what's the length of this, 1 million elements, then fill it up with the input we will pass. Then it loops through the array and fills it up with each element, timesing it by multiple of 2. Then it sums every element inside it and then returns the summation. So we're just doing this just to simulate a very expensive operation. Now you see that it is dependent on the input we send here. So we'll come here and add the input. So now the next thing we have to do is that we need to measure the time or the performance of this function so that we can be able to know the time it takes for it to run each and every one of these inputs passed to it, so that we can now see how the memoization works and the effect it has. So now what we're going to do, we are going to use the performance.now method. Like here, we'll just say performance.now to first start the performance. Now first we are going to check for cache hit. So we'll record the end time cache performance.now. Now we'll now log the execution time spent, execution time. We'll now say end time cache minus the start time. Now we'll now log it. We'll now say, yeah, this is now a cache hit. It took this time, the execution time is in milliseconds. Execution time milliseconds to run. Now input, let's just log the input. So we'll do the same thing here, the time logging here after the execution of the some expensive computation function. Now we'll just say end time. Now this one should be execution cache time, so we can differentiate them. So this one execution time. So now say end time minus the start now from here, and the execution time. So this is no cache, so that we'll know how long it took. So this we did here is just to measure the time it took for this some specific computation, and when there is a cache hit, so that we can see the disparity between two of them when there's a cache and where there is no cache. Mhm. So let's make sure we have everything in place. Now let's run our function. So this will run longer than this, and this will run longer than the last one there. So let's open our terminal and now run test. So sorry, node, should be node. So now let's analyze it now. See, on the first run, 90, there was no cache hit, and it took 21 milliseconds to run for input 90. Now, in the second function, there was no cache hit. Yes, and it took 18 milliseconds to run. The input is 20. Now, for the third, there is now a cache hit because we have already run it here. So we have already run it here. So for it, this one, we had a cache hit here, and now it took 0.01 milliseconds to run. So you see, it didn't take much long, this 21 milliseconds now to run. It took lesser time because it just returned the result from the cache here. It just check the cache and just return the result without uh, this some expensive computation being run. So you see now, this, just imagine the huge time lapse between them. 21 milliseconds, it took the first one 21 and the second one. So you see that it's a very huge performance boost when using memoization.